KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
NEET, JEE, IIT coaching experts from Rajasthan and Andhra Pradesh along with our effective teachers.
Admission registration for classes LKG to +2.
KURINJI Educational Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
In continuation to the last class, in this class we start with 6 exercise problem, right? First you see here, write nuclear reaction equations for different things. So they have given 7 decays here. So for each and everything, for what he is asking, according to the question, we have to answer. Okay, right? So first one is alpha decay of radium, right? 22688. For that we have to write nuclear reaction, right? So we have to write the nuclear reaction. First alpha decay of 22688 radium. Afterwards one by one you can write as the question given, right? As they have given according to the question. And after completion of this, you observe here, right? So one by one, first question and then answer. Okay, see here. So in case of alpha decay of radium 22688, see this. This is what 22688 and radon Rn 22286, and here it is He42, right? So you just see the nucleus, how it is going to modify when it emits one alpha particle, right? Next one, second thing is plutonium, that is what Pu 24294. From this, when alpha particle is going to release, we are getting 238, uranium 23892. Okay, that is what. Next one is, third one is beta decay of, right? Beta decay of phosphorus P 3215, right? And here when we are going to see the beta decay regarding this nucleus, we are getting S3216, right? And then here electron, right? And then like neutrino or anti-neutrino, whatever it may be, right? Here if you see that, so what I am saying is here, you just see the primary particles also in terms of, that is what, like energy, right? And charge also. But in some cases only charge, in some cases it is not. Okay, right? Similarly, you go for fourth one. He is talking about again beta decay of bismuth 21083. Bismuth 21083. Okay, right? Afterwards, see here. So in case of third one, it is beta decay of P3215, no, right? And in case of fourth one, beta decay of, right, Bi 210 and 83. So there we are getting, that is what, neutrino, right, and electron and S3216. Afterwards, fourth one it is what, bismuth, right? So it is Bi 21083, right? Bi 21083. Okay, so that is what, see here, so in case of fourth one, here third one and fourth one both are beta decay only, right? So we should not confuse, the same thing will happen. So that is what on right hand side, see here. So whatever the terms we have here also same. But because this is the base thing is going to change, so he is asking here for P3215, that is what phosphorus, and here he is asking for the bismuth bismuth 210 and 83. That's why, so this is different. That's why here the product is going to change, right? And rest of the part is same. Similarly, next fifth one, it is like beta plus decay, right? Here positron, right? So and because from this carbon it is going to form, right, B11,5, and this is also neutrino. Similarly, sixth one, beta plus decay of TC 9743, and here you can see that is what here, that is E minus plus nu, right? That is in case of sixth one. And seventh one, electron capture of Xe 12054, Xe 12054, right? So in case of Xe 12054, here you can see that Xe 120 plus 54 plus E plus gives rise to that is a new nucleus I 12053 plus neutrino. Okay, so this is about sixth one and seventh one, right? So in chemistry, how we are going to modify, right? In chemistry, how we are modifying, that is what, how we are balancing the chemical equation, right? And similarly here, but there are some differences, both are not same, but there how the process you are going to follow, right? Somewhat surface level, here also the same thing. So every time you have to check the total number of mass number and the total number of atomic number. So when these values are going to change, the nucleus is going to change, right? And alpha decay, and here also alpha decay, it is beta decay, beta minus decay, and beta, it is also beta minus decay, right? Beta plus decay, and this is what electron capture. I hope you usually understood what is going to happen here. So if you take any one, and the same process you can apply for rest of the things. So here alpha decay means here you should have one alpha particle. Here also same thing. So when here alpha particle is emitting, this nucleus is going to modify it into Rn. So here also Pe into U. Here that is what beta minus decay, right? Third one is beta minus decay. Here the same thing. Here you can see you can experience one electron here, right? So here also one electron, right? Here one positron, here one electron, like that. Okay, like that it is going to modify, right? That is the only difference. That is the only difference, right? So rest of the part is same. Rest of the part is same. So what is the rest of the part or basic part? What is the basic part here? In case of, right? In case of, that is what either beta plus decay or beta minus decay, whatever it may be, you have to check all the things. That is, what about mass number and what about atomic number carefully. Okay, so based on that we will decide what is going to form, right? This is all about the sixth problem. It is very simple, but while balancing nuclear reaction we must be very careful, right? So what is alpha decay, what is beta decay, what is gamma decay, already we studied, right? So that is the only thing happens here. So balancing is important. Next, seventh problem, a radioactive isotope has a half-life of, that is what, T years, capital T years, okay, full stop. How long will it take the activity to reduce A 3.125% and B 1% of its original volume, 1% of its original value, okay, right? And this relation, that is what, R by R naught is equal to N by N naught, R by R naught is equal to N by N naught, that is equal to 3.125 by 100, 3.125% means 3.125 by 100, that is equal to 1 by 32, see here, R by R naught, right? It is what, radioactive isotope, it is 1 by 32, okay? So when it is 1 by 32, you can write it as N by N naught is equal to 1 by 2 whole power N. This 32 you can write it as 2 power 5. So finally 1 by 2 power 5, 1 by 2 whole power 5. So you can write it as N is equal to 5. You can write it as N is equal to 5, okay, right? So when N is equal to 5, what about small t? Small t is equal to small n into capital T, right? So when it is small n into capital T, automatically here, it will become 5t years. So that is what small t is equal to 5t years. So this is what this much of time takes, right, to reduce 3.125% to reduce to 3.125%, right. So 5t years time takes the activity to reduce to 3.125%. Next B, right, see here. So the same thing, but here he told 1%, so 1 by 100. Then what about T is equal to 2.303 by lambda. So this relation we know that from theory, right. 2.303 by lambda into log n naught by n, T is equal to. So that is what 2.303 capital T divided by 0.693 log 100. That is what n by n naught is equal to 1 by 100 ma. N naught by n is equal to 100. That is what log 100. And you write down that value and you do the process. Then 2.303 into 2 into capital T divided by 0.693. That is approximately equal to 6.65 t years, right. So it takes 6.65 t years for the activity to reduce to 1% of its original value, right. It takes 5t years for the activity to reduce 3.125% of original value, and it takes 6.65 t years to reduce to 1% of its original value. Okay, right. Next, see here, that is 8th question. The question is big, and you listen carefully, then we will go for answer. The normal activity of living carbon containing matter is found to be about 15 decays per minute for every gram of carbon. It is like information or is a fact, right. The normal activity of living carbon containing matter is found to be about 15 decays per minute for every gram of carbon. Okay, right. This activity arises, right. This activity arises from the small proportion. This activity arises from the small proportion of radioactive C14 present with the ordinary carbon isotope, that is C12. Okay, right. When the organism is dead, its interaction with the atmosphere ceases and its activity begins to drop. So here atmosphere means what? Which maintains the above equilibrium activity. Okay, right. So he is saying that when organism is dead, its interaction with the atmosphere, right, ceases and its activity begins to drop, right, full stop. From the known half-life, that is what, 5730 years, right. From the known half-life of C14 and the measured activity, the age of the specimen can be approximately estimated, right. From the known half-life of C14 and measured activity, the age of the specimen can be approximately estimated. That's what we are calling it as carbon dating, to find out the age of the, that is what, older stones, and to find out the age of the, that is what, old aged trees, right. So there we are using the process, that is what, carbon date, right. This is the principle of carbon dating used in archaeology, right. Suppose a specimen from Mohenjo-daro gives an activity of 9 decays per minute per gram of carbon. Estimate the approximate age of the Indus Valley civilization, right. So here he told that from the known half-life of C14 and measured activity, you can estimate approximately, right. Here he is asking to estimate, that is what, Mohenjo-daro, right. Suppose a specimen from Mohenjo-daro gives an activity of 9 decays per minute per gram of carbon. Estimate approximately age of the Indus Valley civilization. Okay, that he is asking to Fine. Okay, right. And you know, this problem is about carbon dating. Here he is asking to calculate, that is what Mohenjo-daro specimen by giving an activity, and already we know that half-life, right? And finally we are going to estimate the approximate age of the Indus Valley civilization. Okay, right. Given normal activity R0 is equal to 15 decays, right? 15 decays per minute. It is the normal activity. Here they have given. And next, right? Next thing is present activity R is equal to 9 decays per minute. 9 decays per minute. Okay. Present activity R is equal to 9 decays per minute. 9 decays per minute. Okay. See here. T off is equal to. So finally, T off, that is what half-life, 5730 years. You know this relation even from previous problem also we used the same, that is R by R0 is equal to N by N0, that is equal to N0 into e to the power of minus lambda t. Here N0, these two will get cancelled. Finally, R by R0 is equal to e power minus lambda t, right? Then you can write it as 9 by 15 is equal to 9 by 15 is equal to e to the power of minus lambda t, or e power lambda t is equal to 15 by 9. So taking normal logarithms, that is log e, right? Log e, here also e power lambda. See here. So just we are writing the value, that is what log e power lambda t to the base e is equal to log 15 by 9, because we got e power lambda t value, no, that we are writing here to the base e. Or the same thing you can also write lambda t log e to the base e, lambda t. Here we have to use the formulas for logarithm, right? So lambda t, see, you know, log a power m to the base e is equal to m log a to the base e. This is the formula, logarithmic formula. From that formula I am writing here lambda t log e to the base e is equal to 2.303 log 5 by 3 here base 10. It is what 5 by 3 to the base 10. Okay. And afterwards, you know, if you do this calculation, it will be 0. Here if you do this calculation, finally you can get it as small t is equal to small t. This is so this side is this one and this side is this one. Finally, small t is equal to 0.5109 by lambda. 0.5109 by lambda. Next, as T of is equal, is a formula, you know, T of is equal to 0.693 by lambda. That implies small t is equal to 4224 years. 4224 years. So whatever he is asking, that is estimate the approximate age of the Indus Valley civilization, means that is 4000 years. Okay, in exact 4224 years. Okay, so this relation we know, no, T of is equal to 0.693 by lambda, right? So and we also know that t, small t is equal to 0.5109 by lambda, right? So in place of lambda you can write this value. So finally, and what is T of means already given 5730 years, right? And this relation and this relation and this value, that is T of is equal to 5730 years. Finally we are getting small t as 4224 years. Okay, right. Next problem, that is problem number 9. Obtain the amount of cobalt 6027 necessary to provide a radioactive source of 8 millicurie strength, and they have given half-life for cobalt, that is what 5.3 years. 5.3 years, right? And you don't confuse while using small t and capital T, it is the time taken. See, it is not the half-life. Here we calculated time for Indus Valley civilization, right? It is half-life. Okay, and this is also half-life, right? And in this 9th problem, he is asking amount of cobalt necessary to provide a radioactive source 8 millicurie strength. Okay, and in this problem itself, you know very well what are the things they have given. It is capital R, 8 millicurie, that we can convert it into disintegrations per second, because for example it is 10 power minus 3 amma. So the same thing you can write it as 8 into 10 power minus 3 into 3.7 into 10 to the power of 10. So 1 curie is equal to 3.7 into 10 to the power of 10 disintegrations per second. So if you convert this value into disintegrations per second, you will get it as 29.6 into 10 to the power of 7 disintegration per second. Now come to this point, R is equal to lambda n, that is 0.693 by T of into n. N is equal to same thing, n is equal to R into T to the power of 1 by 2 by 0.693. So write down the value of R that we converted into disintegrations per second, that is 29.6 into 10 to the power of 7 disintegration per second, and T of is 5.3 years. That also you have to convert into seconds, that is 5.3 into 3.16 into 10 to the power of 7 seconds divided by this value. So that we are getting the value of n as 7.15 into 10 to the power of 16 atoms. Okay, right. And next, you see here, as 60 grams of cobalt, as 60 grams of cobalt contains Avogadro number 6.023 into 10 to the power of 23 atoms. So the amount necessary to obtain a source of required strength, the amount necessary to obtain a source of the required strength is equal to, same thing, that is what 60 grams, 60 into this value, that is what 60 into 7.15 into 10 to the power of 16 divided by Avogadro number 6.023 into 10 to the power of 23 will give us finally 7.123 into 10 to the power of minus 6 grams. 7.123 into 10 to the power of minus 6 grams. So this is the amount which is necessary to obtain a source of the required strength. Okay, right. And these relations are known relations only, right? The small thing is we have to understand what he is asking, and we have to identify what they have given, and substituting the given things we are getting n value, right? And from n value finally we are getting that value of amount of mass. Okay, right, mass or amount of substance. Next problem, 10th problem. The half-life of strontium SR 9038 is 28 years. What is the disintegration rate of 15 milligrams of this isotope? Okay, and first here we have to write the given things, that is what T of is equal to 28 years, that we can convert into seconds, 28 into 3.154 into 10 to the power of 7 seconds, and mass is 15 milligrams, that is equal to 0.015 gram, and capital M is equal to 90. And now number of atoms in 0.015 grams sample of strontium 8038, n is equal to, so we are going to find the number of atoms. So small m by capital M into Avogadro's number, right? So you write down the values, and then you will get it as, right, here you will get some value, otherwise directly you can substitute this here, right, because it's the number of atoms. Finally activity of the sample R is equal to lambda into n, that is equal to 0.693 by T of into n value already we had, so by substituting this one and T of also, that is what 28 years, finally we are getting these many disintegrations per second, and disintegration per second is nothing but becquerel, 7.877 into 10 to the power of 10 becquerel, that again you can convert into curie, right? 7.877 into 10 to the power of 10 by 3.7 into 10 to the power of 10 curie, that is equal to 2.13 curie, right? So in this class we discussed 5 problems, from 6th problem to 10th problem, right? In the first problem, we had nuclear reaction equations for alpha decay and beta plus decay, beta minus decay for different nucleus, right? At last one we also discussed that electron capture of Xe 120 and 54, right? And 7th one, there itself we found that time, that is what for given activity. And next in next problem we discussed like carbon dating related problem. And in 9th one, right, we calculated the amount, that amount of cobalt necessary to provide a radioactive source of 8 millicurie strength, okay. And in the last problem we calculated activity of the, we measured the activity of the sample R, right. So we got it as 2.13 curie, okay, right. And watch this video again and again, ma. So because it is online class, I mean YouTube class, no. So how many times you want, you can watch the same video, right. So after watching many times, you will get clarity, right. If you have any doubts further, you can approach. Thank you. We will continue in the next class.